It's time to wrap up what we have learned in nuclear physics. Okay, so this would be nuclear physics wrap up. Okay. Okay. What we have learned is basically in chapter 1. Okay. Chapter 1 we have learned pretty much about nuclear structure. Okay, structure. Okay, so yeah, we know that this is our nucleus. Okay, and inside it we have protons and neutron. So this is proton and probably this is neutron, and like that. Okay, so probably this is proton, this is neutron. Okay, so it's pretty simple. Okay, we have learned about mass spectrometer. So it's like this. Okay, and we have the opening over here. So we are going to put the atom inside. So this is the source atom. We're going to put inside, and then we are going to vaporize it. Vaporizer. Okay, so this is vaporizer into ions. So this is the ion. Okay, this is ion. So it's ion. So this is vaporizer. To vaporize the atom into ions. Then we have sort of accelerator region. So this accelerator region. This is accelerator. So it will accelerate using E field, strong electromagnetic field. Sorry, electric field. Okay, E field. So the atom will enter here, this region, and then it will get accelerated more faster. Okay. And then we have the region of magnetic field. So this is strong magnetic field. So this is magnet, north south. This is magnet. Okay, strong magnet. So it provides the magnetic field. Okay, magnetic field into the page, for example. So this is uniform magnetic field. Then the particle will travels along this and then get deflected okay, into what we call the detector. This is detector. This this is detector. So the detector will detect the presence of this ion, and then it will separate them into the portion of charge to mass ratio. Okay, the reason why you have to vaporize it here, because we need to have the atom to be charged. Okay, because the atom is usually neutral, which is in the sense that it has no charge. But the thing is, the mass spectrometer requires us to separate these isotopes of atom into mass charge to mass ratio. Okay. Alright, so that's the mechanism. So the equation is very simple. So here is the region of what we call velocity selector. The region of velocity selector. Velocity selector. Okay. That the equation is very simple. We are going to derive the equation. The charge per mass ratio. So first, we consider. Okay, we know that the B field first. The B field is given by the magnitude, basically. Is Q, V is the velocity, and B. So Q is charge. Okay, charge. So we can insert as E. So E is charge, elementary charge. Okay, and then what else we can do? Okay, okay, we can say that conservation of energy, maybe we can use that first. Because in the velocity selector, in the accelerator here, the ions get accelerated. First we need to consider the E field. Okay, it is get accelerated. Why? Because the electric field, the strong electric field being influenced to the ion particle. Okay, so the potential energy, okay, so potential is electric field divided by distance. Okay, or we can say that it is work done to move 1 coulomb per charge. Okay, is charge. So we can say that EV is work done. Okay, and then this work done is transferred into kinetic energy, or KE, which is 1 by 2 mv square. Hence we have EV, so V is the potential, 1/2 mv square in velocity selector it will experience the centripetal force, hence B field is F centripetal. So Q EBV equals to 1/2 mv square over r. So again cancels one of them and make V as the subject, I guess. V is EP R over M. We subs into 1. So 1 is basically where 1? We're here. So EV sama dengan 1/2 mv square. So EB R of M square. So how to find this? So EV equals to ME square B square R square over 2M square. We can cancel this, that, hence E over M is a 2V over BR square. Okay. Right. So that's a little bit about that. What else we have learned about liquid drop model? Liquid drop model. So the equation is given by the binding energy of a nucleus is the volume term. A is the mass number minus surface constant, A to the power of 2 by 3, the Coulomb constant, the Coulomb term, Z square, A to the power of 1 by 3, asymmetric term, A asymmetry, Z minus N all square divided by A plus and minus the delta. So the delta is plus 11 MeV if the nucleus is even, minus 11 MeV if odd nuclei, odd, and 0 if odd A. Okay, which means the mass number is odd. So this is actually to find the binding energy of the nuclei. So we can use mass defect. So mass defect is E equals to mc square, delta mc square, which is m is the difference between the mass number of the nuclei. So we can say it's mass before or mass before or mass final minus mass initial c square. Okay, what else we have learned is we have learned about packing fraction. So the packing fraction is defined as F equals to the mass defect M divided by the mass number A. Okay, so pretty simple, and this is equivalent to the mass of the nuclei divided by A minus 1. Okay, or M minus A divided by A. So this is equivalent. Okay, let's see. We have learned about the Heisenberg uncertainty principle. Heisenberg uncertainty principle tells us about delta E dot delta T is basically less than or equal more than or equal to h bar over 2. And we also learn about the range. Okay, the range, or what we call the effective range of the weak force. Okay, we have the formula as R, the range, is equivalent to C, the speed of light, times the delta T. Okay, and then we have E equals to mc square. So we can use these three things to find the perimeter that we want. It depends basically. Okay, so this three formula is important. We have learned about what else? We have learned about quantum mechanics of the deuterium, so deuterium problem. So when we have a finite square well, so this is V naught, negative V naught, this is 0, this is the potential, this is R, this is R, small r axis. So the energy provided is less than the potential. So this is the bound state, E less than 0. So we'll see the particle will oscillate inside the well and will decay outside the well, like that. It will decay here. So it penetrates the barrier basically, because this is quantum mechanics. Solving the Schrödinger equation. So over here solution of the Schrodinger equation is psi region 1 r is a constant sine of k r, and over here the solution is psi 2 r equals to c e minus kr. Okay, if you solve the Schrodinger equation, i.e. if you get the solution, so the Schrodinger equation is basically tells us minus h bar square over 2m d square dx square d square over dx square plus the potential is we got the e psi. If you solve this, you already get the solution, which is this and that, and then just a matter of substitution. Then you solve the boundary condition, which is at the boundary psi 1 equals to psi 2, and the first derivative of the psi is equivalent to the first derivative of the psi 2. Okay. We have learned about quantum number, spin angular momentum. So spin angular momentum is s h bar s plus 1. So this is the spin quantum number, this is the spin angular momentum, so it's different. And also the orbital quantum number is big L, so this is big S, this is small s, then we have orbital angular momentum is big L, h bar L, small l, L plus 1, and also the total angular momentum is I, is given by h bar j plus 1, so j is the total angular quantum number. Okay, and the main important equation is the total angular momentum is L plus S. Very important. We have shell model, so shell model is the model that explains the stability of the nucleus, and it also gives us the reference to determine the spin, okay, the spin total angular momentum of the nucleus. Okay. So we have magic number. So magic number is a number which is special. For example, we have 2. Okay, 6, sorry, 2, I forgot already. Wait up. We have 2. Okay, 2 8. Okay, 2 8 6 20, I guess. 20 28 50 82 126. So this is actually represents the number of nucleon, either the proton number or neutron number. For example, if you have an atom that has what? That has 10, sorry, not 10, that has 10 proton and 10 neutron, which means it has 20, no, this does not work, it has 20, maybe 20, I don't know, 8 and 6, so it has 8 proton and 6 neutron, which means 8 tambah 6, 8 plus 6 is 14. So we call this as magic number. So the proton possess the magic number. So if the atom has this magic number, either the proton or the neutron, we call it it has higher stability than the rest. But if we have, for example, so this is magic number proton, because proton is 8. Okay, in the list of the magic number. But instead, if we have an atom with 8 which is 16, so this is oxygen basically, oxygen, so 8 proton 8 neutron, so this is double magic. So double magic, which means both proton and neutron has the magic number in it. So the importance of the magic number is the magic number, if the magic number presents as the proton number or the neutron number of the atom or of the nucleus, it is more stable than not having it, than the rest, than the other atom. So if double magic, which is double stability. Okay, we've learned about Norden's rule. So Nordheim's rule, Nordheim's rule. So this is for odd nuclei. So it says that if we have J1 plus J2 plus L1 plus L2 is odd, then we need to do J plus 2 to find the spin of the nucleus. Okay, the total spin, or I, okay, total angular momentum, I. Okay, if it is if it is even, then we need to do j1 minus j2 and take the positive number. Okay, that's easy. We have also learned about quadruple moment. Quadruple electric moment, quadruple electric moment, which tells about the stability state. Okay, electric quadruple moment. So it tells us about the shape of the nucleus and also the distribution of charge. So it is given by a simple equation. We usually use Q as the electric quadruple moment. 1 over E integrate 3z square minus r square, the charge density times the cube r. So we integrate in 3 dimensions. And when we solve the integral, basically we get Q is, I forgot this, 2 over 5 z b square minus a square. Okay, so when b is greater than a, so we have q is greater than 0. So we have this to be prolet. So our shape of the nucleus will be prolet. So prolet will look like this. This is our z-axis, and our shape will like this. So this is prolet, and when q less than 0, q smaller than 0, which is b is smaller than a, so we will shape like this. Okay, but what if q equals to 0, which means our shape is perfect sphere, like this. This is sphere. This is sphere. So this is oblate. We call it oblate. And this is prolet. And you need to remember it is based on z-axis over here. Okay. So it determines the distribution of charge. Well, I think that's actually there are so many, but what I've been discussing just now is just the important subtopic. Okay, so yeah, that's all. I think I'm talking so much today. So yeah, so that's all for the wrapping up for the chapter 1. Later I will continue if I got time to do. Thank you.